This material has been reproduced and communicated to you by or on behalf of the Australian National University, in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
Okay, hi everyone. Welcome to week 3. Hopefully your workshops went okay. There was a few hiccups, but they should be smooth from this week onwards. I've changed my consultation hours to Wednesday, so 2 to 4 p.m. Wednesday. You don't need to book an appointment. My office is in the Hannah Neumann building, room 2.73, so it's on level 2. If you have any questions regarding the course content, you can come and see me. Otherwise, you can ask online or to one of your demonstrators. Okay, so today we're going to continue on with relations and functions, especially the functions part. And we're going to study specific types of functions and prove whether they're that type of function or not. Okay, so some properties of functions. You've probably seen this before from maybe high school, but it's important to get it all well defined now. Okay, so if we have a function from A to B, we say it's one-to-one or injective or is an injection when for every 2 elements in A, if they're not the same, this implies that they go to different places in the codomain. So maybe an image to visualize this. If you've got A here and B here, the function f is mapping here, and then particular elements. If it's an injection, then if they're different elements, then they're going to get mapped to different places in B. And if it's not an injection, then we're going to have 2 elements mapping to the same place in B. So this definition is probably the good way to prove something is not an injection. So you find 2 elements that are different and then show that they map to the same place. But if you want to prove a function is injective, it's usually easier to do the contrapositive. So for all elements, if they map to the same place, then they're actually the same element. So let's work through an example. So we've got a function on the natural numbers, and it just takes the square of the natural number. And the question is f injective? And the answer is yes. And this is where our sort of like logical proof structure is going to come in handy. So what we need to do is clearly identify this logical structure on how we're going to prove it. If you're getting practice, then write the structural part of the proof first, and then try and complete the middle of the proof. If you've got more experience, then you can work through it directly. Okay. So if we want to show it's injective, then we want to show that for all integers n1 and n2, if the functions map to the same place, then they're in fact equal. So what we're going to do is we're going to let n1 and n2 be in n, suppose our hypothesis, fn1 equals fn2, and then we're going to prove that n1 equals n2. So this is our sort of logical structure. So what we need to do is add in the proof. So let's go through the proof. So I've got our first assumption. Now, since this should be an N2, so since Fn1 is equal to Fn2, this means that N1 squared is equal to N2 squared, because that's just the definition of the function. We rearrange it so that there's a 0 on this side. The reason I'm not taking a square root is it's a little bit awkward to assume that we know what a square root of a natural number is, because sometimes it might not match, like map to a natural number. So this is the more formal way to do it. So rearrange, factorize the difference of two squares. Since this n1 minus n2 times n1 plus 2 is equal to 0, that means either n1 minus 2 is equal to 0 or n1 plus 2 is equal to 0. And that's just because the product is 0 if and only if at least one of the factors is 0. And since n1 and n2 are both positive, this means that the sum of n1 plus n2 is larger than 0. So this means that this part can never be true. So the only solution is going to come from this part here. So n1 minus n2 is equal to 0, and therefore n1 is equal to n2. And this means that f is injective, because we've proven that for any elements in the natural numbers, two elements in the natural numbers, if they map to the same place, they must be equal. Okay, so now sort of the same example, but we're going to change the domain a little. So we've got G from Z to Z, and we're going to define it by Gn is equal to n squared. Is G injective? The answer is no. And the way that we prove that something's not injective is we're going to give a counterexample. And so if we have a look at the plan, if we want to disprove for all n1, n2, this implies this. We want to prove the negation. So the negation of this whole statement that we have, which is equivalent to, instead of for all, we take there exists and we bring the negation on the inside. And then the next step, since an implication, if you have something like A implies B, this is logically equivalent to not A or B. So that's the intermediate step inside here. We've changed this into not this or this. And then when we take the negation of that, then this or becomes an end, and the negation in front of this one disappears, and the negation in front of this one appears. And so what we need to prove is there exists an n1 and n2 in Z such that both they map to the same place, but they're also not equal. So two distinct elements mapping to the same place. And I think it should be pretty obvious how you come up with two different numbers. So you just take some number in Z and take its negative. So some number in Z that's not 0. So you could use 2 and minus 2. If you square those, you get 4. So therefore, G is not injective, but you could say give 1 and minus 1 as examples, or minus 4 and 4 as examples. You can just choose anything. So in some ways, proving something's injective is maybe harder, but sometimes it's difficult to find two different numbers. So sometimes proving something's not injective can be difficult depending on the function. Okay, so now we've got the next property of a function, which is surjectivity. So if we've got a function from A to B, we say that f is onto, or f maps onto B, or f is surjective, or f is a surjection. And when do we say this? If for every element in our codomain, so every element in B, there exists an element in our domain that maps to B under F. So the way that you should think about this is you have your A, you have your B, and then we have our function F. And then if I draw in every element of B here, there exists some element here which will map to this one here. There's one that maps to this one here, and so on. So every element in B gets mapped to by something in A. And so an equivalent statement is F is surjective when its codomain and range are equal. Okay, so let's do an example on proving a function is surjective. So we've got a function h from the natural numbers to the Cartesian product of the natural numbers with itself, and we're going to define it by n goes to n and n plus 1. And the question is h surjective? And the answer is no. And so the way that you prove something's not surjective is you give an example inside this set, which doesn't get mapped to. So there's heaps of choices, but a simple one is 1, 4. You can't write this as the form n plus 1. And since 1, 4 is inside this set, and there's no element that maps to 1, 4, we can say that h is not surjective. So I guess this example is a little bit tricky because maybe you're not used to working with Cartesian products much, but remember this set, n times n, is like all of the ordered pairs of natural numbers with a natural number. Yep. You can always make a function surjective by just changing the domain to the range. Yeah. And the same goes for injective. So you can always change a function if it's not injective. You can change it to an injective function by restricting the domain to something smaller. Okay, so now let's look at another example. This one's a little bit tricky because it's a piecewise function. So we let j be the function from natural numbers to integers, and we define it by this piecewise function, which is n over 2 minus 1 if n is even. And just to make sure that this makes sense, since n is even, this is going to be a whole number. And so it is going to be inside of z. And then if n is odd, then we're going to define it as the negative of n plus 1 over 2. And that's also going to be well defined as a member of this, because if n is odd, then this will be an even number, so we can divide it by 2 and still be a whole number. So the question is j surjective? And the answer is yes. It's going to be kind of a case-by-case sort of proof. And again, if you're not familiar with doing proofs, then maybe you should write down the logical structure of how you want to prove it. Maybe consider the negation and disprove that instead. And So the way that you decide is you check both ways and see which one seems easier. And then, yeah, try and complete the middle of the proof. So the statement we need to prove if we are asking is J surjective, and if we say yes, then what we need to prove is for all elements in the integers, so that's positive and negative numbers, and 0, there exists a natural number such that the function maps to this integer. And, well, we can write the negation of this. So the negation would change the for alls to an exists, and the exists to a for all, and then Jn not equal to Z. I guess what we're trying to do is decide, is it surjective or not? I've already told you it's going to be surjective, but so first maybe compute some numbers to get a feel for what the function's actually doing, because this function is a little bit tricky. So let's start with the first number in the natural numbers, which is 1, and then compute a few more. So J1, since 1 is odd, this is going to give us minus 2 over 2, which is minus 1. When n equals to 2, then we go into this side, and it's going to be 1 minus 1, which is 0. And 3 gives us minus 2. N equals 4 gives us 1. And if we keep going, then you can see that it's like oscillating between a higher magnitude negative number and then a positive number that's like 1 less in magnitude, but it's increasing every 2 steps as well. So from this, I would say that you can see that the function's going to be surjective, because you can see that we're going to slowly cover all of the integers. So let's try and prove the yes. So let Z be an element of Z, and what we need to show is there exists an input that maps to Z. And we're going to split it into 2 cases, when Z is greater than or equal to 0 and when Z is less than 0. And the reasoning behind that is in our calculations here, you can kind of see that there's this oscillating pattern between the positive and negatives depending on whether the input's odd or even. Okay, so if Z is larger than 0, then we need a number that is n, which is equal to 2Z plus 1. Therefore, if n is in the natural numbers and n is even, oh wait, sorry, I've got my logic the wrong way around. We're going to let a number n equal 2z plus 1. Then, since n is in the natural numbers and n is even, that means when we substitute n into our function j, then we're going to substitute it into this component here. So we substitute 2z plus 1, simplify, and we get z. So that's straightforward. So if you've seen like maybe like inverse functions, then you can kind of see what we're doing here. But then in the case that z is smaller than 0, we're going to let n equal minus 1 plus 2z. Then since n is in the natural numbers and n is odd, and you can see that n is odd because it's a multiple of 2 plus 1. So therefore it goes into this component here. If we just simplify down, if we substitute n in, then we come out as z again. And so this covers all possible cases of an integer, because we've got the non-negative integers and then the negative integers. So in all cases, we have an input that maps to z, and so therefore the function is surjective. I guess maybe the misleading thing here is we kind of just come up with these numbers, but what we're trying to do, what you'd probably do in the side working is you'd just say that this is equal to z, have z equal n over 2 minus 1, z plus 1 is equal to n over 2, so n is equal to 2z plus 1. And so then we will use this substitution. And that's the same way that you come up with this one here. Just let z be the function, consider when n is odd, rearrange, and then substitute that, whatever you get, and that should give you the z that you're looking for. Does anyone have any questions about surjective? Yep, so to know if a function is surjective or not, then you probably need to understand the codomain. So if you take a function that takes any integer as input and outputs the absolute value of the input, then f is surjective if the codomain is n, but it's not surjective if the codomain is z. So if you change the codomain, then it might not be surjective or not. Okay, so the next property of a function is bijective. So if you have a function f that goes from a to b, we say that it's bijective, or that f is a bijection when it's both injective and surjective. And in this situation, what you get is that a and b are actually in one-to-one correspondence if f is a bijection. So the way that you can think about a bijective function is if you've got your two sets a and b, then for every element in a, there's a unique element in b that it maps to because it's a function, and there's actually, for every element in b, there's a unique element in a because it's bijective. So for every element in b, there's a unique element in a that maps to it. But the usual way that you prove a function is bijective is just by doing the two steps. First prove it's injective, and then prove it's surjective. Yep?
I want to ask if just like the element, there is because there is element
No, so something that's impossible for this is that you can't have another element here mapping to this same element into B. It won't be bijective. So maybe to understand why you get this one-to-one correspondence, so surjective says for every element in B, we're going to be able to map to something from A to B. And then the injective is giving us that uniqueness. So there's a unique element from A that maps to this element in B. Cool. Okay, so another thing you can consider is applying function and then applying another function afterwards. So let's take three sets now. So we've got A, B, and C, and they're all subsets of some universal set U. If f is a function from A to B, and g is a function from B to C, then the rule A goes to the function f applied to A, and then g applied to the f of A, defines a function called the composition of g and f. And we denote this by g circle f. So g circle f of an element in A is equal to the function applied to A, f, the function f applied to A, and then the function g applied to fa. And maybe like a little picture. We've got A, B, and C. So f is a function from A to B, and g is a function from B to C. And yeah, so if you take an element in A, it gets mapped to some element in B, and then G maps it to something like this. So we can just rewrite this as A to C instead. One thing to note is, I guess this B and this B maybe don't need to be quite the same if you want to compose functions, because maybe the function f doesn't map to all of B. You just need to make sure that G is mapping from something that contains the range of f. And then another thing to remember is the order of composition matters. If I did write f circle G, then this wouldn't make any sense because G is mapping from B to C. And then F is mapping from A to B, so you can't map an element of C to A using any of the functions that we've defined here. So this is a function G to B, G from B to C, and then we have no function from C to A. And yeah, so if I applied the function f to this set C, then it doesn't make any sense because we don't know anything about how C is related to A. Okay, so let's look at an example. If A is the set cat, dog, chicken, and we let f be the function that sends A to a natural number, an element of A to a natural number, and we define it by the rule that the cat maps to 70, the dog maps to 90, and the chicken maps to 50. And then we take another rule, we take the function g, and the function just multiplies our number by 3. Then, yeah, g composed with f is well defined, but f composed with g is undefined. Because, yeah, so f takes a to, so maybe we say f of cat equals 70, and then if we take g after that, then g is here, and so then we just multiply by 3, so we get 210. But if we looked at f circle g, and, well, g maps from a natural number, so let's take the number 1, then this is equal to f of 3, and the function f on a natural number is not well defined, so because the function f is only mapping from this set of animals. So it's really important that you get the ordering of functions right, and like that the sets are mapping to the correct places. Does anybody have any questions about compositions of functions? I guess so. Like, the one exception is maybe you could have a function like if I define f as from the natural numbers to the natural numbers, and we take n goes to n squared, and then I take g And this is defined on, I'm going to call it x. And this maps also to the natural numbers. And the way that I'm going to say x is actually a subset of the natural numbers, and it's the subset that I'm defining x as is all of the square natural numbers. Then if we take a square natural number, and I'll just call it s, then this maybe this gets mapped to, I don't know, 2s. Even though x is not equal to this, the range of f is equal to x, and so it's fine. Does that kind of make sense? You can compose g with f. So if you take this, this is going to be equal to g of n squared. And since x contains all of the square numbers, then this is well defined, and it just goes to 2n squared. And, well, this doesn't have exactly the same set here. So the natural numbers versus the squares of natural numbers. So it doesn't necessarily have to be the same if you want to compose functions. They just need to match up in the sense that the range of f goes into the domain of the next function, g. Okay, so our all of the previous definitions that we've made is going to help us define an inverse function. So you can remember when we were studying relations that we had this inverse relation. So if we take two subsets of a universal set U, remember that if we have a relation from A to B, then the inverse relation from B to A is determined by the rule A is related to B if and only if B is related to, inversely related to A. And then we have a theorem that says if we have two subsets of the universal set and we let our function map from A to B, so f is a function from A to B, then the inverse relation, f inverse, is indeed a function. So that's important. So since f is a function, it is a relation, so we know there's an inverse relation. The question is the inverse relation actually a function as well? And the answer is yes, if and only if our f is bijective. So that's a very important theorem to know. And so if f is bijective, then we can define f minus 1 as it being a function as well, and we'll call them inverse functions, and we'll say that f is invertible. Okay, so if, for example, I give you a function, I say, is it invertible? Then what you need to prove is that it is a bijection. And then we have this nice property of invertible functions. So if we have a set A, first I need to define something. So if we have a set A, we define the identity function on A as this I sub A, and it sends elements of A to A, and it just maps them to the same thing. Yeah, so it maps A to A. So it's basically doing nothing. And the idea is, if our function is a bijection, then we have these two composition properties. So the composition of f inverse with f is equal to the identity on A, and the composition of f with f inverse is the identity on B. And maybe it's useful to just write up what this looks like in pictures. So f is mapping to B, and then f inverse is mapping back to A. And so if we go like this, and we take an element inside of A, then this is going to be equal to A. And then if we do the other way around, so we start with an element in B, we apply the F inverse, we go to A, then we go back to B with F. Then if we have an element inside of B, we can apply F inverse to it. Oops. And then we can apply F to it after that. And this is just going to be equal to B. That's just explaining why this one is the identity on A and this one is the identity on B. Okay, so I'm just going to do sort of an extended example. The point of this is to kind of highlight this idea of like restricting the domain or the codomain to make the function either injective or surjective and therefore bijective and then invertible. So if we have a function from the reals to the reals and we define it by this x squared again, can we find an inverse of this function f? And my answer is no, because we can always find an x that maps to the same, we can find two distinct elements of our real numbers that map to the same place, and what they are is any positive number x and negative, and then you take the negative of it, and maybe I should make a correction and say we can't choose 0. That wouldn't be an example. So what this means is f is not injective. Because we've got two different elements in the codomain mapping to the same place in two different elements in the domain that are mapping to the same place in the codomain. Okay, so the next example is basically the same function, but I'm going to restrict the codomain a little bit. The domain a little bit. So we're going to take just the non-negative numbers. And so we're going to define this as g, and gx is equal to x squared. And my question is, can we find an inverse of g? So is g bijective? And again, the answer is no. And the reasoning is there is no element in our codomain. There is no element in our codomain such that gx. Oops. I've made a mistake. This should be this thing here. So there's no element in our domain that maps to the element -1 in our codomain. So what I'm saying here is G is not surjective. I guess I could probably note here also that F is not surjective for the same reason. So this one is both non-injective and not surjective. Whereas this G here that we have is actually injective, so we can prove that it's injective. But it's not surjective, so that means it's not bijective, and therefore we can't find an inverse. So I'm going to try again. I'm going to restrict the codomain now to be the non-negative numbers as well. So let h be the function that squares a number. Can we inverse h? And the answer is yes, because h is bijective. And so to be able to prove that, what you're going to need to do is prove it's both injective and surjective. And then my question is, what is the inverse of h? And I'll leave that as an exercise to work this all out, but maybe I should write that h minus 1x should work out to be equal to the square root of x. Now, there's another way we could sort of restrict our first function f to get a invertible function. And this one is k. So instead of restricting the domain to the non-negative numbers, I'm going to restrict it to the non-positive numbers. So k is still this function that squares a number. And similarly, it's bijective, so therefore you can inverse it. But I guess the lesson is, because I've restricted this domain in a different way, the inverse function is actually going to be slightly different. So the inverse function, k minus 1 x, should be the negative of the square root of x as a function. So I'll leave that as like an exercise for you guys to work out. It'll take too long to go through in a lecture. But yeah, if you have any questions, then feel free to ask. Okay, so just to end this lecture, I'm going to give a definition of a kind of a function that may appear, I think, in later weeks. We might use it for something. So we've got a set B, which is just made up of 0 and 1. We've got an n, which is just some positive integer. And we define a set Bn as the Cartesian product of B n times. So maybe just to be clear, B0, oh, no, B is not B0. B1 is equal to B. B2 is equal to B times B. B3 is equal to B times B times B. So remember, these are just sets, and so this is a 1 tuple, this is a 2 tuple or a double, and this is a 3 tuple, which is a triple. Well, the elements of it are those. And then what we're going to do is, for each n in n, we're going to define a function hn, which takes something inside of Bn, Cartesian with this again. So I guess this is kind of a little bit funky. You could even nearly think of this as, I'm going to draw this as squiggly equals. This is kind of the same as b to n. But so we're taking the Cartesian product of this set Bn and with itself, and we're mapping into the non-negative integers. And the rule is, if we take an element from here and here, the number of coordinate positions which differ is sort of the number that we're going to count. So maybe to do a simple example, we'll do HST, and I'm going to let S equal 0, 1. So this is an element of B squared. And I'm going to let T equal 1, 1. And this is also an element of B squared. And so what this function is counting is, we look at the first component 0 in the S. It's different from the first component of T. So that's going to give us a 1. And then we look at the second component, it's a 1. This is the same as this one, so we're going to plus a 0. And so the value of this H2ST, when we've got S and T equal to these things, will be 1. yeah, the question is, with what have we defined above? We've actually defined, we've defined infinitely many sets defined by like taking Cartesian products. We've defined for each natural number a different type of function which counts the differences in the tuples. Okay. So these functions that we've defined, these h1, h2, and up, are called the Hamming distance functions. And so for each integer n, Bn is the set of n tuples of binary digits. So for example, in B6, we could have an element that looks like this. And yeah, so we're just comparing how often they agree. And so the outputs is going to count the number of times they agree and then not count when they disagree. Oh wait, sorry, I got it mixed up this time. So it compares when they agree and then it outputs the number of coordinates in which they disagree. So it's counting how many times each coordinate is different. So in this case, the first coordinate is different, so this gives us a 1. The second coordinate is the same, so that doesn't give us anything. The third coordinates are different, so that gives us a 1. The fourth coordinates are different, so this gives us another 1, and then the fifth coordinate is the same, and so that gives us nothing. So we've got 1 plus 1 plus 1, which equals 3. Okay, and you can actually define like relations on these functions and stuff. So that's what the next slide is going to be about. So consider the relation. So it's going to be a subset of B3 times B3. So this is just B times B times B. And we're going to say xy is inside of this relation if and only if they differ exactly once. And my kind of example is to construct the digraph for this relation. And there's kind of an easy way to do it. And my hint towards this is you're going to add directions and stuff, but it should look something like a cube, and the cube is coming from this 3. And then my question is, how would you create a similar relation on Bn times Bn, and then what would that digraph be looking like? So that's probably a good thing to think about, and this should appear in later weeks where we're going to look at like applications of this. So that's it for today, and if you have any questions, come and see me.